All right, so one of the ways that we're going to try and get around dealing with this messy integral to calculate the electric field is by using Gauss's law. And so Gauss's law actually tells us about what's going on with the electric flux. So Gauss's law says that the electric flux through any closed surface is proportional to the net charge enclosed by the surface. So mathematically, it's just a statement that the electric flux is proportional to the charge enclosed. And so what that tells us is, well, now we have two ways to calculate the electric flux. One is we can do this double integral over all of our little area elements and E dot dA when we have a constant field in a flat surface. This just becomes E dot A. But either way, that's one way that we can calculate the electric flux. But Gauss's law says you've got a second choice to calculate the electric flux. You can calculate it by basically just counting up the charge enclosed within your surface and then dividing by the permittivity of free space, which we've seen before. This is epsilon naught. So a couple of details here. One is this I can use for any surface. This I only get to use with a closed surface, and we'll talk about that in a second. But what's nice is it says if what you're interested in is the electric flux through a closed surface, then as a general rule, Gauss's law gives us a much simpler way to calculate the electric flux. We don't need to deal with this double integral. All we need to do is count up the charge enclosed by our surface and divide by epsilon naught, and that's going to give us the exact same value. So Gauss's law can be incredibly powerful in terms of calculating the electric flux. It says instead of doing this double integral, which can be very complicated, it involves this dot product, so I care about the relative direction between two vectors. I care about the magnitude of the electric field over all my little surface elements. This can be an incredibly complicated process in terms of trying to calculate the electric flux. Gauss's law says there's a much easier way. Just go count up the charges enclosed inside your surface, divide by epsilon naught. So again, a couple of the details here. The first one is it says through any closed surface, right? And so closed surfaces are basically just things that you tend to think of as shapes. So notice just a flat circle, that's an open surface. Flat square or rectangle, whatever, that's an open surface. Even if I have this sort of hemispherical bowl here, right? Just take a sphere and cut it in half. The fact that I leave this side open makes this an open surface. And as a general rule, because Gauss's law requires a closed surface, we're not going to be able to use Gauss's law if we're interested in the flux through surfaces like these. Now there's one subtle way we'll come back to in a second where we might be able to use Gauss's law to think about what's going on some square, but we'll come back to that one in a second. Instead, Gauss's law applies to closed surfaces. So here I've got some sphere that's a closed surface, and I can count up all the charges that are inside my sphere. Here I happen to have what's known as a toroid or a donut, right? And again, I can have charges inside the toroid. Here I've got a cube. Obviously that's a closed surface where I can have charges inside my cube. So these are the types of surfaces that are closed surfaces, and so therefore Gauss's law is very well suited to calculating the electric flux. Now the one way that we can get away with using Gauss's law to think about the flux through just a single square is by thinking about the flux in certain situations through a cube and then saying that, well, the square is just 1/6. It's one of the 6 sides of the cube. And so there are situations in where there's going to be enough symmetry that we can use a cube and Gauss's law with a cube, where we pick a cube as our Gaussian surface and use that to figure out the flux through a single side of the cube therefore thinking about the flux through what really is an open surface. But that's a pretty rare case. Okay. The other detail. So what we're going to do is we're basically going to pick Gaussian surfaces. And so you notice here I happen to pick a Gaussian sphere, and I've placed it around the positive charge. And so what you notice is that, again, Gauss's law is telling us about the electric flux. We said the electric flux is telling us something about how the electric field lines are piercing our surface. And when we had an open surface, the fact that we could basically pick the area vector on either side of our open surface to basically line up with the electric field meant that we never really had to worry about whether we were having positive or negative electric flux. But with a closed surface, positive and negative electric flux are actually trying to tell us something. So you'll notice here's a situation where basically all the field lines through my Gaussian surface are pointing outward. So they're going outward through my Gaussian surface. This is a situation where I have positive electric flux. So what this means is I have a positive value for the electric flux through a closed surface when more field lines leave the surface than enter it. One way that we will often talk about this, or that you may hear people talk about this, is to say that that means your Gaussian surface contains a source. Well, what if I switch and put my Gaussian surface over here? So again, I've got my dipole. Here I've got my negative charge that I've enclosed in my Gaussian surface. And so now what I notice is all my field lines are entering the surface rather than leaving it. So this is a situation where the electric flux is actually going to be negative. Right? The charge that I enclose here has a negative value, so my electric flux is going to have some negative number divided by epsilon naught. So my electric flux is negative in this case, which tells me that I've got more field lines entering my Gaussian surface than leaving it, and this is what you might hear referred to as a sink. So I can have sources and sinks. And then if I happen to pick a Gaussian surface that encloses both, well, now if you think about the charge enclosed, I've got some positive charge, I got the same amount of negative charge. When I add that together, the net charge enclosed within my Gaussian surface actually happens to be 0. And so here's a situation where the electric flux is 0. And so what that means is I've got an equal number of field lines entering and leaving the surface. So over here on this side, all my field lines are leaving the surface, but there's a field line over here where I've got basically the same strength, the same relative intensity. They're all entering the surface, and so when I add them all together, what I find is that there's a field line over here that's going to cancel out every single field line over there, and so the net number of field lines leaving or entering is actually 0. I've got the same number leaving as entering, and so my electric flux through my Gaussian surface here is 0. Right? So again, this is why Gauss's law gives us a really easy, powerful way to calculate the electric flux by simply counting up the charge inside our Gaussian surface. Now, it can also be very useful when we have high degrees of symmetry to calculate the magnitude of the electric field. So this is one of the ways that we're going to get around that ugly integral for calculating the electric field. And so you notice if we think about the two equations that we were looking at on the very first slide, right, here was an equation for the electric flux, and all we've done is say, well, because Gauss's law requires, or is talking about the electric flux through a closed surface, this circle here in our double integral is just telling us that we're talking about a closed surface rather than an open one. And so this integral, right, that's one way to calculate the electric flux through a closed surface. Gauss's law says count up the amount of charge contained inside your surface divided by epsilon naught. That's the other way to calculate the electric flux to the surface. And so these two things have actually got to be equal to each other because they're both just ways to calculate the electric flux. And what you'll notice is if we can simplify this integral, then what we're left with is a fairly basic expression on the left that just says the magnitude of the electric field times the area of our surface has got to be Q enclosed over epsilon naught. And so this gives us an easy way to calculate the magnitude of the electric field by simply dividing Q enclosed over epsilon naught by the area of the surface that we've picked, of our Gaussian surface. But this only works if we can simplify the double integral. So what are the two things that we have to do? Well, basically, we've got to have the electric field be constant over all our area elements so that we can pull it out and be left with simply the double integral of our little area elements dA. And so because we've got E as a vector with a dot product, there's two things, sort of two criteria that we've got to meet to simplify this integral. The first is the magnitude of the electric field must be constant over the entire closed surface. So we've got to pick exactly the right Gaussian surface so that the electric field, the magnitude of the electric field is constant at all points on our surface. And then we've also got to pick exactly the right Gaussian surface so that the relative direction between the electric field and every single area element is going to be the same. So our electric field vector has always got to point the same relative to our little area elements dA over the entire surface as well. So if we meet those two criteria, then this integral simplifies and we're left with EA equals Q enclosed over epsilon naught, and this now gives us a fairly easy way, basically just an algebraic way, to calculate the electric field. So this is why, if we have the right situation with the right degree of symmetry, we can use Gauss's law to quickly and easily calculate the magnitude of the electric field. Now, what are these certain situations? Well, there's basically three types of symmetry that we're going to end up dealing with the Gauss's law problem. The first one is spherical symmetry. So you've got spherical symmetry when your electric field either radiates outward from a single point or inward towards a single point. So in this case, because I have basically a positive spherical charge, I've got an electric field that radiates outward away from the center of that point. And so when is it that I'm going to have spherical symmetry in my problem? Well, the types of charges that give us spherical symmetry are point charges. I can have charged spheres, and these can be spherical insulators or spherical conductors. I can have charged spherical shells. Again, those can be insulators or conductors. So these, when my charges are arranged in these sorts of situations, then I've got enough spherical symmetry that Gauss's law becomes useful. The second type of symmetry where Gauss's law can be very useful is when I have cylindrical symmetry. So when is it that I have cylindrical symmetry? Well, basically, when you've got an electric field that radiates outward from or inward towards a single line. So here, think of this as a cylinder, right? And that cylinder, you make it really, really narrow. It looks like a line. You make it really fat. It looks like a big fat cylinder. Somewhere in between, you might call it a rod. But all of those are situations where, as long as we make this cylinder long enough so that we don't have to worry about fringing effects at the edges, then I've got spherical symmetry within the problem. So we'll talk about infinitely long, and really by infinitely long we just mean long enough to not have to worry about fringing effects at the edge. But infinitely long lines of charge, or infinitely long charged cylinders, or infinitely long charged cylindrical shells, infinitely long charged rods, all of those are going to give us cylindrical symmetry, so that picking our Gaussian surface as a Gaussian cylinder will be useful. And then the third type of symmetry that we'll run across is planar symmetry. So planar symmetry is you've got electric field lines radiating either outward from or inward towards some plane, some sheet, right? And so you'll have the types of charges that'll give us planar symmetry, so this should read planar symmetry here, are either going to be infinitely large charged sheets or infinitely large charged plates. And again, the infinitely large says that we're far enough away from the edges that we don't need to worry about fringing effects at the edges. So if we're very close towards the center of some normally sized charged sheet, then we can act like it's infinitely large, and we can use Gauss's law. And so we'll be able to take advantage of using Gauss's law in special situations to figure out what the electric field is. And so the sort of crux of Gauss's law is it's almost always helpful if you're interested in the electric flux. If you're interested in calculating the magnitude of the electric field, then you've got to have a lot of symmetry in the problem, and you've got to figure out just exactly the right Gaussian surface to pick that simplifies the integral so that you can calculate the electric field easily. And that's going to be a lot of what we're going to concentrate on when we're actually working Gauss's law problems in class.